Hey everybody, this is Larry. This is day 29. And this and the, day 29 of the Leetcode Weekly Challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about today's farm. And we have a weekly problem as well, so you'll see that if you like to. But yeah, let's take a look. Minimum difficulty of a job schedule. So we schedule a list of jobs in D days. Jobs are dependent. You have to finish at least one task every day. The difficulty of a job schedule is the sum of the difficulties of each day of the day jobs. The difficulty of the day is the maximum difficulty of jobs done on that day. Okay, so you have the max of each day, and then you sum up the max of each day. Is that what they're saying? Okay. I mean, that generally feels very binary search-y. But maybe not. Maybe I'm kind of okay. Let's see. Return the minimum difficulty. Okay. So when would you have -1? What does -1 mean? Oh yeah, you have to have a job for each day. That's a very weird way of doing it, maybe, but I don't know. All right. So day is equal to 2. Okay. I think I misread. Oh, I missed the to work on the I've job. You have to finish all the jobs J, because all the jobs are dependent. For some reason, I read this as jobs are independent, and I just couldn't figure out why they need to do all this stuff. And then okay, that makes sense. Okay, that makes sense. Okay, yeah, because otherwise you would just sort and greedy is what I was going to say, but then I just couldn't figure out like looking at these forms. But yeah, okay, so then now it becomes maybe dynamic programming, right? Because in a way dynamic programming, of course, is just a brute force, knowing that you're brute forcing the same stuff, so you save down the results, so you don't have to do as much work, right? And what would the states be in this particular one? Well, a straightforward one is indexing on job difficulty. I don't know if job difficulty survive does anything, but the other thing is noticing that D is less than 10. That usually is, I wouldn't say a giveaway, but it's definitely something that you're trying to exploit, right? Like we see something that's 10, then maybe we can exploit it. And I think, yeah, maybe initially my inclination would be have an index, and as usual, as we talked about the last couple of days, if you have been watching the last couple of days and not just this problem, then a subproblem, the way that I think about it is that you're trying to, the index just represent the suffix of the inputs that you're trying to do, right? And then maybe you have days left, so maybe you have another D here, maybe D left, just to kind of crank it out. And I think that's already enough to get started, because the number of states here so far is not that bad, because index is going to be 0 to n, D left is going to be 0 to D, and in practical terms it just means 300 times 10 is the total number of states, number of states, and so here just a little bit of the rough estimate is that you can do another O of n, and that'll be fast enough, right? Because it's just 300 squared times 10, which is just shy of 1,000,000, right? Yeah. So then here now, then if index is equal to n, maybe if we have, yeah, if index is equal to n and D left is equal to 0, that means we gotten every job, and we've done every job, and every day we had a job. So then here we can return 0. Otherwise, then if only one of these is true, then we return infinity, right? Because that means that you have failed, because, well, you don't have any days left, which means that you still have jobs left but don't have any days. That's not good enough. Or you have finished all the jobs but you don't have any days left. So yeah, so one of these is going to be infinity. I think that's already good enough for us to kind of do a sort of a brute force. So then now you have j in range from how do we know? So we want to include index +1. So maybe something like depends how you want to write it precisely. Like you get to choose the bounds, right? So it's not that much of an issue. But for me, maybe I would write something like and this is the part where I skipped ahead a little bit, or I skipped a little bit and didn't go back, which is kind of define what this means, right? So this means get the minimum total difficulty of the suffix of job difficulty starting at index, right? And the D left I think is more obvious, so I'm not going to write it. But that allows you to kind of remember that what you're considering, right? And here it's kind of I'm going to write it a little bit suboptimally first, so don't worry if you're at home. It's fine. But then the idea here is that, okay, let's say now we want to brute force. Okay, take job index ... j inclusive, right? So basically now you want to take all the jobs from index to j, and there are a couple of ways you can actually write this. But for example, you can maybe do something like max of job difficulty from index to j +1 because you want it to be inclusive. So then now you have get min of j +1 because it included j, so you don't need to do j again. D left -1. So that's the sub problem plus this thing, and then now you could compare it to the best that you've gotten, and there you go. That is close-ish to done, but not yet, and we start at 0 and D is the answer. So we could give it a quick run. I don't know if this one, I think I have to, okay, I forgot about the -1 case. So R is equal to this thing. If R is infinity or greater, it shouldn't be greater, but why not? Then we return -1, and look, it's great, it's good. The problem, of course, is that it's going to time out. There are a couple of issues with this one. First, it's going to be memorization. As we said, we do index of n, we do O of d. So, and the big thing about memorization is that for every same input, we're going to get the same output. So if we do that, then we should save down things that we're going to call repeatedly, which we might. So yeah, which now allows to define an upper bound on performance. So that's basically what we're going to do. Oops. Something like this, right? And I know, every time I don't explain it, people ask me about it, but I feel like I explain it every other day. But I don't know, sometimes it's just tough to explain every time. But I do have, two things to make it explicit. You don't need to use two things. You can use one cache if you like. I just do it for teaching reason, for just for so it's easier to kind of you don't have to make any assumptions around anything. It is perfectly, like if you write this, you don't have to ask anyone what this means. It actually, the code becomes self-documenting, right? So that's why I kind of write it this way. Whether you're smart at home, so you can, if you like, you can improve on it if you like, and yeah. So this looks better. Is it good enough? Probably not. I'm going to YOLO submit, but we'll talk about an optimization after this, right? And why? Okay, well, actually, it turned out to be good, which is actually surprising. Maybe not. I don't know. But okay. And actually even faster than last time I did it. Okay, so what is the complexity so far? We'll have to go over this. I actually thought it made time out, to be honest. But yeah, so the number of states, the number of possible inputs, it's going to be D times N. Number of inputs. Each input, how much work does it take, right? It takes work. Well, there's an O of N loop, so you may assume O of N, but inside this O of N loop, there's also this max loop, right? I mean, it's a one-liner, so it doesn't look like a loop sometimes, especially if you haven't, if it's new to you. But that means that this is actually an N square loop. So what happens is that this actually takes O of D times N times O of n squared for each work. So that means that total time complexity anyway is going to be O of d times n cubed, right? And of course, that is actually too slow in theory. There is some there are a couple of things, right? One is that not all the states are possible, so it's not going to be a hard n cube. And also, of course, max in Python is also very optimized, I think. Maybe I'm wrong on this one, actually. But it is and slices and stuff like this. They're much faster than usual quote unquote Pythonic operations. So yeah, but still, this is the complexity, and as you kind of add more n's and more d's and whatever, you could kind of see that thing grow if you plot it over a graph, right? That is the thing. So one thing, of course, to note is that okay, well, you can actually do this in a it's not a sliding window, but just like as you kind of like a rolling window, maybe that's the way to go. A rolling max, right? Because you can kind of rewrite this, and certainly there are ways you can rewrite this to even incorporate, if you really like dynamic programming, you could rewrite this as a dynamic programming, right? Because, for example, what does this mean, right? This means getting the I don't know where to put this, but yeah, you want to get the max of job difficulty from index to j, right? Inclusive, and of course that just means max of job difficulty, same index, j minus 1, and job difficulty of j, right? So these two set of numbers, and of course you see that there is a sort of a recursive relationship here. So you kind of define this recursively, and of course, you know, if you do this recursively, then you could memorize it, right? Right? Yeah, so you can do that, but of course the analogous to bottom top-down memorization is bottoms up, though it's not technical. I don't know. Anything could be dynamic programming if you want to call it that. After all, the name itself doesn't even mean anything anyway, really. So yeah, but yeah, for example, you can just do a rolling max is what I would say, right? So let's just say current max is equal to negative infinity, and then here we have current max is equal to max of current max job difficulty of j, right? And then now you can just do current max, and you'll be pretty okay, pretty Gucci at this. Well, pretty Gucci if you kind of remember to close your parens. Yeah, and that would give us a mid. Hopefully, it's a little bit faster. Yeah, actually, you know, twice as fast, though. You know, and of course, now that you got rid of one of the loops, you can kind of just, you know, each one does O of n work instead of n squared work, and now this is O of n d times n squared, and you're a happier boy, or you know, however you want to identify yourself. I'm a happier boy. Anyway, yeah, that's all I have for this one. I think, unless it's wrong. Apparently, people are gotten even much faster. Is there a much better way? I don't know, maybe. I mean, you could do this bottoms up as well, I guess. But and if you do it bottoms up, you may notice that is it easy to do bottoms up? Yeah, it actually should be pretty straightforward to do bottoms up. And then you may notice that one of the dimensions is not necessary, and then you could do the space optimization. You can kind of notice this if you just have have practiced a lot and have experience, but also just taking a look at this formula, and you notice that you always use the d left minus 1, and in that way you can kind of optimize. You can think about optimizing that dimension away, but by doing it in that order, right? Because every input where you have d left, you only care about d left minus 1, so now you do it in the other way, right? Building up from d left is equal to 0, and then 1, and then so forth. I mean, you know, that's all I have for this one. That's all I have for today. Let me know what you think. Yeah, happy holidays again, everybody. Hope y'all, I mean, New Year's is coming soon. 2023 has been kind of a weird year for me. Hopefully it's less weird for you. I don't know what I'm talking about, but that's all I have for today. Stay good, stay healthy, to good mental health. I'll see you later and take care. But before that, I'll just show you the code one more time. This is the top. This is the memorization. And that's all I have. Have a good night, everybody. Bye-bye. My mouse is like not working.